Hello, class. I'm going to go ahead and go over a COREC number 5 for statistics, and it's involving scientific notation. So this is from your workbook for statistics. It has to do with the COREC, and you know, they don't have page numbers. I apologize for that, but it's next one after order of operations PEMDAS, and this one's called scientific notation. Okay, so I have the same information on this page. I actually had it enlarged only because this was really light and small. So it's the same information except it's just larger font. So I went ahead and did that for this page. So it says that scientific notation is a means by which we can write very large numbers and very small numbers without having to write numerous zeros in the number. When this is true, this is true. So when you're converting to scientific notation, here are the steps they say to follow. They say that if the original number is greater than 9, the exponent for the power of 10 should be positive. Its absolute value is equal to the number of places the decimal point has been moved. Okay, all right. So what I probably should do is also write down an idea about scientific notation. So I'm going to add something to this page here. Scientific notation does have a particular format. So the format for scientific notation kind of looks like this. A times 10 to the n. That's what scientific notation looks like. It has this format. And really A is a number between 1 and 10. That can include, that may include 1, but it should exclude 10. Okay, so it's a number between 1 and 10. It could actually equal 1. So 1 times 10 to the fifth power, for example, but it cannot include 10, cannot include 10. It can include 1, but not 10. And then any number between 1 and 10. Okay. When it says a times 10 to the n, know that n is an integer. And integers look like this. So like dot dot dot, like -3, -2, -1, 0, 1, dot dot dot. Okay, those are integers. So n can be an integer. So n cannot be a decimal, n cannot be a fraction, but n can equal an integer. -1, -2, -3, -4, -5, and so on. 0, 1, 2, 3, 4, 5, and so on. Okay. All right. So write that down, then pause if you're still writing, pause. But I'm going to go ahead and read the second part, number 2. And remember, I enlarged it, so I have it written here on this page. So it says that, still talking about changing things, converting it, making it look like scientific notation. It says that if the original number is between 0 and 1, the exponent for the power of 10 would then be negative. Okay. its absolute value is equal to the number of places the decimal point was moved. Okay, so here we have two examples here, and this is called scientific notation. See this? These are called, this format is called scientific notation. Okay, it's got that format. This is your A. Here's your A times 10 to the n. So um, notice how A is a number between 1 and 10. 8.9 is a number between 1 and 10. And notice how the n in 10 times 10 to the n, notice how the n is an integer. -5 is an example of an integer. Okay, this result 4 times 10 to the -8. So A is a number between 1 and 10. And then this exponent is an integer. N is allowed to be an integer, and -8 is an integer. Okay, so it meets the format A times 10 to the n. Okay, now so this is what your problem began with here, this decimal value. So if I look at my place value, it has 1, 2, 3, 4, 5, 6 place values. So let's see. Let me see if I can find my place value chart. Let's see. Look for my place value. Yeah, let me show you this. So I have a place value chart here. So you see I was counting 1, 2, 3, 4, 5, 6. So if I look at my place value chart, see here's the decimal. 1, 2, 3, 4, 5, 6. So see that? Looks like that's the millions. See that? Millions place. So here's your decimal point. 1, 2, 3, 4, 5, 6. That's the millions. So we have tens, hundreds, thousands, 10,000s, 100,000s, millions place value. So then this would be read out loud. 89 millions. 89 millions. Okay. Now this one over here is very small, even smaller. 1, 2, 3, 4, 5, 6, 7, 8. So let's see if my little chart goes up to that. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yes. See, that's 100 millions. So 1, 2, 3, 4, 5, 6, 7, 8. That's 100 millions. 100 millions. So this problem is out loud read 400 millions with a THS at the end. Okay, so both of these, you would want to make these into a scientific notation. So they're saying that these original numbers, that these were numbers between 0 and 1. Okay, so it's a value somewhere between 0 and 1. Okay, and so they're saying that the exponent for the power of 10 is going to be negative. So you see how both of these have little negatives, power of 10? Its absolute value is equal to the number of places the decimal point was moved. So here you want to relocate the decimal point so that it's sitting between the 8 and the 9. You're going to create a number that's between, for scientific notation, a number that's between 1 and 10 is what's required. So if you move it in front of the 8, it's too small. So if you move it here and you make it 0.89, that would be considered too small. And if you move it behind the 9 and you make it 89, then it's too large. It's too large. It's either too small or too large, okay? So there should just be one place to put that decimal point, and you want to move it between the 8 and the 9. And so you want to move it 1, 2, 3, 4, 5 times, 5 places, okay? So you moved it 5 places, and you want to make this a negative exponent. And that's what this is saying. It says the exponent for the power of 10 is going to be negative, okay? So when we check this here, the reason why this is a negative exponent and not a positive is because you're multiplying 8.9 times a power of 10, and it's a very small power of 10, 10 to the negative 5. This is a small number. So the effect that this has is it also makes this small. So this negative exponent, when you multiply this by 8.9, it's also going to make this small, okay? And same thing over here on this side for this problem. You move it 1, 2, 3, 4, 5, 6, 7, 8 times. See, 8 times. Anywhere else is not sufficient. If you move it in front of the 4.4, then this is considered too small. And yeah, so that's why you want to move it behind the 4. The 4 is after the 4 is just fine. Okay, that's a number between 1 and 10. And that's a requirement for a times 10 to the n. A's got to be a number between 1 and 10. It can actually equal 1. Okay, it cannot actually equal 10. It can be very close to 10. And then times 10 to the negative 8 because they moved it 8 times. Yeah, moved it 8 times, okay? So the effect that this negative power has on 4 on this A is that it also makes it smaller, okay? So that's correct. And let me see if we can kind of check this. Let me just see if we can check on the calculator. If we just try to check your answer here, I have 8.9 times 10, and then I'm going to raise it. So I see this caret key here, raise it to the negative. So the negative is down here, negative 5th power. And let's see, let me hit enter. Okay, so the thing is, like, this is on scientific notation, okay, because it says 8.9 e to the negative 5, 8.9 e to the negative 5. So that's uh, that means that means this times 10 to the negative 5. So e to the negative 5 means times 10 to negative 5. So they're not showing that. Let me just try. I have another basic calculator. This is like we usually use these in the liberal arts math classes and the college algebra class. Let me just try that on this. If I try 8.9 times 10 raised to the negative 5 power and hit enter. See, this does show the equivalent of that here. Okay. So I don't know, maybe on our settings, let me just look at our settings here and see if I can, is there a way to change? If I go to math, no, not math. Let me go to mode. Here it says normal, scientific and engineering. Let me just see what happens if I put it on sci, hit enter. Okay, so let me turn it back off, second off. And didn't turn it off. I was trying to turn it off. Second off. Okay, turn it back on. Let me see. 8.9 times 10 raised to the negative fifth power. So let me see if that, nope, it still gives us that. Okay, let me try mode one more time. Because let me go back to normal. It was normal to begin though, wasn't it? So second, turn it off. Let me see. Nope. Let me just try the engineering route. Let's see. Mode, engineering, change it to engineering. So I just moved it down. Engineering, turn this off, turn it back on. 8.9 times 10 raised to the negative fifth power. Nope. All right. Nope. Okay, so that's fine. I was just trying to see if I could, let me change this back to normal. See, float here. Is there anything on? Let me, on the float, let me highlight the 9. Let me see if that will do it. So it's on normal. Let me highlight the 9. Turn this off. Turn it back on. Let's see. 8.9 times 10 raised to the negative fifth power. Nope. Nope. What that does is that puts all these there. Okay, that's fine. I was just trying to show something like this on the calculator, but that's okay. It's fine. So let me go back to mode. And I think I'll leave that at 9 there. It's fine. Okay. Okay. All right. So they have examples here for number 2. They didn't put any examples for number 1. They just have a comment there. Let's see. Okay, and then next, let's see. Next we go to numbers 1, 2, and 3. So this is part 3. So this says that if the original number is between 1 and 10, so like I guess like this 2.5, it's a number between 1 and 10. The exponent on 10 is 0. So they have this 2.5 equals 2.5 times 10 to the 0. And they're telling you that 10 to the 0 is 1. So we should be able to show that on this calculator. Let's see. 10 to the 0. 10 raised to the 0 power. Yep, is equal to 1. 10 raised to 0 power is equal to 1. Okay, that's true. Okay, so then this case scientific notation is not needed. Okay. Interesting how they're saying that. So scientific notation is not needed. Yeah, so they're saying that you can 2.5 I guess can just stand on its own then. Because 10 to the 0 by definition is 1. 2.5 times 1 is 2.5. So they're saying then that when this is 0, that you don't actually have to have it in scientific notation. That's what they're saying. So, okay, so keep that in mind. All right, so now let's go to some problems here. There we go. Write these numbers in scientific notation, okay? So write the number in scientific notation. So we have this hundreds, thousands, millions, 93 million miles. This is the approximate distance between the Earth and the Sun. And they want you to write this in scientific notation. That means that they want this to have the format a times 10 to the n. And remember, here's your restriction on a. A has to be a number that pretty much is between 1 and 10. It can actually equal 1, but it cannot actually equal 10. So it gets very close to 10, like 9.9, 9.98. Okay, so here's your restriction on A. And of course, N is an integer. So N is an element. It's an element of the integers, dot, 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 -2, -1, 0, 1, dot, 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 for example. So n is an integer. Okay, and now you're going to write this in scientific notation. Okay, so I'm going to relocate the decimal. Right now it's way back here, imaginary, and I'm going to move it all the way over here so that it sits between 9 and 3. So I'm going to relocate the decimal so that I have 9.3 times 10, and I need a power. Okay, and anything else is either too small or too big. If I move it in front of the 9, then that's like 93 cents. That's too small. Okay, remember it. Remember, it's got to be between 1 and 10. And if I move it behind the 3, 93 like that, then that's just way too large. That's just way too large, too big. It's got a limitation is up to no more than 10. Okay, up to 10, less than 10. So forget about 93. So yeah, the best place to put it is 9.3. Now, how many moves that you need? 1, 2, 3, 4, 5, 6, 7. We need 7 moves. 1, 2, 3, 4, 5, 6, 7. So the thing is, you're thinking, do I go with a positive 7 or do I go with a negative 7? Okay. Well, if you go with a positive 7, what will happen is this is a large power of 10. This is a 1 with 7 zeros. That effect on A will make A bigger. And see, that's what you want. See, that's a large number. If you go with a -7, so 10 to the -7 is a small number. And what happens is that will make this even smaller. 9.3 will become even smaller. See, and you don't want a small number. This was a big number, hundreds, thousands, millions. Yeah. So you don't want a small number. And then if we check it like on a basic calculator, I was having issues with the TI-84, but if I just check that 9.3 times 10 raised right here, see, raised to the 7 power and then equals. See, that matches 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We get the same thing. They don't have the commas. Okay, but you're able to check it on a basic scientific calculator here. And if I try to match what it said, that one matches, I think, this first one here. Remember, they didn't have an example here, but see, it says the exponent for the power 10 is positive, and that's what happened here. This exponent was a positive 7. So it says that this happens when the original number is greater than 9. So this is, oh yeah, this is the original number. Oh yeah, it's way bigger than 9, 93 million. So yeah, it was way bigger than 9, greater than 9. The exponent for the power 10 is positive. Its absolute value is equal to the number of places the decimal point was moved. Yeah. Yeah, so it was moved 3, 6, 7 times. Okay. Okay, now if you look at B, it's a very small number, and this has to do with the mass of a dust particle. Very small number. And kg should be what? Kilograms, right? Kilograms, kg. This one was miles, mi. Okay. This one's meters per second. And this one's just meters. Okay. So let's see how many. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is like, if I read this out loud, this is like 753, and then you need a place value. I think this one does go off my chart. Remember I had a little chart I showed you? 3, 6, 7, 8, 9, 10, 11, 12. So let's see. Here's my decimal point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, well, since it's just one more larger, then I know, see, this is billions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I needed 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, it's the next period over. And I can't tell here, but I can tell by looking at this. See, there's a little bit of similarities, a little bit of similarities here. Thousands, millions, billions. So I can see that I can, because I see this, it's trillions. So this would be the trillions, but with the THS at the end. So this is 753, but what place value? 753, and that would be trillions with the THS at the end of that. Okay. All right. And I can, if you want, I can also do this. So you can, pause the screen if you want, pause it if you want to write those down. Okay, and then there's one little bit that goes off the chart there. You can pause the screen and write that down. Okay. Okay. So what we're going to do is make this into scientific notation. So here your decimal is going to relocate. You're still relocating the decimal. So you still want to relocate your decimal, but it's going, let's see, in the opposite direction from part A all the way over here. And you're going to move it in between the 7 and the 5. So this becomes 7.53 times 10 to the power. Yeah, because anywhere else it's going to have issues. If you decide to put the decimal in front of the 7, that's just too small. See, see the restrictions got to be at least 1, equal to 1. This is more like 75 cents, right? So it's shy. And if you move it behind the 5, 75.3, or if you move it behind the 3, then you have 753. So either way, but the issue with these is these are too large. These are too large. So whether you work with 75.3, that's too large because it's bigger than 10. And 753 is also too large. Okay. So this is good. And then when you count 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 6, 9, and then we stopped here, 10. So this should be 7.3 times 10 to the 10th. And then remember, you have to think do I need to go with the positive power of 10 or a negative power of 10? If you go with a positive power 10, this is a large number. It's a 1 with like several zeros right behind it, like 10 zeros behind that, right? So it's a very large number. So the effect on multiplying by a very large number is it will also make this large. And you see, you don't want that. You don't want this to be large, see? So that's why you should go with the negative number. Okay, times 10 to the negative 10, because this is a small number, and the small number, when you multiply it times 7.53, it also makes that smaller. Okay, so if I just try and check that here, 7.53 times 10 raised to the negative 10 power. See how I did that? If I hit enter. Okay, yeah, so see, this one just has too many digits here. See, there's 3, 6, 9, 12. Yeah, so this one, let me see if I just check out the mode. Yeah, you see, it looks like I only can go up to 9 on that. So that's okay then. Not a big deal. That's okay. Okay, so two more here. Let's see. Here, so 3, 6, 9 digits. So let's see, 3, 6, 9. They're going this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. So see, this looks like it's in the millions. So this looks like it's 300, 300 millions. 300 millions, okay. So you want to move your, this is the speed of light. How fast is light move per meters per second? So, so then you want to relocate your decimal point, because right now it's back there. If you don't see it, it's understood to be in the back. So you want to move it just so that it's correct. Anywhere else, if you move it in the front of the 3, that's just too small. If you move it um, um, behind one of those zeros, like here, right here, behind that 0, that's too big. Okay, so just move it between the 3 and the 0 there. So 3 times 10, and then count 3, 6, 7, 8. So it looks like you have 3 times 10 to the 8. This is a large power, and when you multiply that, it will make this large also. Okay, those are ideas, right? Your properties, that's ideas. Okay, and then D, we're going to move the decimal point all the way. Let's see, you wanted it between a number between 1 and 10. So you actually could move it right here between the 1 and the 7. There should just always be one good spot to move it. If you move it in the front of the 1, that's too small, because that's like 17 cents. And if you put it in the back of 7, the decimal point, well, actually they have, let's see, if I put it, yeah, if I put it behind the 7 like that, if I put it like that, the problem with this is too large. 17 would be considered too large, okay? So we're going to go with 1.7 times 10, and when we count, 1, 2, 3, 4 times 10 to the 4, 0.7 times 10 to the 4, okay? All right. And I guess I should also include my labeling, right? So this looks like this is meters here based on that. This one was the meters per second. It looks like the second one labeling was, let's see. So maybe I should box these. Excuse me. So let's see. Where's the other answer? Here it is right here. And that's kilograms. So I can highlight those two. Okay, so I have a note also to say that that only one decimal point is allowed in a number. Okay, because sometimes people, when they write their answers up, sometimes they want to have two decimals. Like they want to keep the original where the original decimal is at, but then they want to blend that in with this new move. And so you shouldn't do that. Okay, you shouldn't do that. So just only one decimal point is allowed in the number. Okay, excuse me. The other thing I have to say is assume the decimal point is at the end of the number if you don't see it. Assume, excuse me, assume the decimal point is at the end, is at the end of the number if you don't see it. Excuse me. Okay. So write that down and pause if you need to, if it's going to take you longer. Okay, and I think, let's see, I have one more page of writing for this. Page, just says slide 25. Let's see what it says here. And I don't think I enlarged that one, that page, but it's big enough though, I think. It says converting scientific notation to standard form. Okay, and sometimes they call it decimal form. So if you kind of look at your problems down here, you'll see that, see, you're going to convert this, which is, you're going to convert this to see, excuse me, sorry, convert this to decimal notation, okay? Or sometimes they call it standard notation. They do use those. They do use those, both of those words, okay? So it says number one, it says if the exponent on 10 is positive, move the decimal point to the right the same number of places as the exponent. Add zeros as necessary. So if the exponent on 10 is negative, move the decimal point to the left the same number of places as the exponent. Add zeros as necessary. Okay, all right. So we'll make use of that. So if we look at your problem, these three A, B, C, D problems. A says 3 and 52 hundredths, right? 3 and 52 hundredths, tens, hundredths, times 10 to negative 5. So this is this small power of 10. So this excuse me, this small power of 10 does have an effect on the A, because this is still A times 10 to the n. So this small power of 10 makes the 3.52 smaller too. So this is a small number and you multiply it times this, that makes this small also. So this small power of 10 makes 3.52 smaller too. Okay. So here we'll have to, since it's going to make this smaller, the only way to make this smaller is to move your decimal to the left, and that will make it smaller. So then in our answer here we have 0 point, and I'm going to move this to the left 5 times. So this counts as one move, but then I need 4 zeros. 1, 2, 3, 4 zeros. Because see, I need 5 moves, so this 3 counts as one move, but I also need these 1, 2, 3, 4, and then there's my 3, and then 5, 2. So 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Yes, and then 3, 5, 2. You have 4 zeros, and then this 3 counts as if like a 5th move. So you got that accounted for. Okay. 4.6 times 10 to the 4th. Okay. This is a large power of 10. Excuse me. So this large power of 10, what does it do? It makes 4.6 larger too. Okay. So this large power of 10 makes this, when you multiply it, makes this large also, makes this larger. So that means if I'm going to make this larger, I'm going to move my decimal point. I'm going to have to move it to the right to make this large. 4, 6, and then I have to make this large. So I'm going to move to the right, but 4 times. Excuse me, 4.6 times 10 to the 4th. So it makes this large. So I want to move this to the right 4 times. So this 6 counts as one move, but then you do need, instead of 4, you need 3 other zeros. Okay. Okay, part C, 9 times 10 to the negative 12. Okay, so remember, like we said on A, this is a small power of 10. 10 to the negative 12 is a small number. So the impact it will have on this, it will also make 9 small. And the only way to make 9 small is if you move to the left, okay, to make that small. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So they're all accounted for. And then 9 times 10 to the negative 12. So this is a small power of 10. It's going to make this smaller. So the only way to make this smaller is to move this decimal point 12 times. But this does count for one of those moves. So I do need 11 zeros. I don't know how many did I have. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 10, 11. Okay, so this is a small number. When you multiply this effect on 9, it will also make 9 small. The only way to make 9 small is to move your decimal over to the left. So you're going to move it to the left. 12 times. And this, excuse me, this die will count for one move. But you need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, it looks like you've got them. Then that 9. Okay, so let me double check that. It looks good. 11 and then the 9. Okay, that's good. Okay, and then let's see. 1 times 10 to the 15. Okay, so what do they want you to do here? 1 times, anything times 1 is itself, right? 1 times 10 to the 15. Let's pause. 1 times 10 to the 15. Okay, so here I have a note that this is a positive, this is a large, right? This is a large power of 10. So it's gonna make, it makes one large 2. Okay. So the only way to make this large is to move your decimal right that many times, 15 times. So your decimal is right here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. I was at 9 zeros. 9, 10, 11, 12, 13, 14, 15. Okay. So put my commas 1, 2, 3, comma, 1, 3, comma, comma. Okay, so if I check that, let's see. 1, 2, 3, 4, 5 periods of zeros. 1, 2, 3, 4, 5 periods of zeros. Yes, and then the 1. Okay. All right. Trying to see what else. What else do I need to say about that? But I think that's fine. You also have some videos. Remember, you have a list of videos. So if you need supplementary, besides this lecture, you're always welcome to get into your Connect Math. There's a page in Connect Math that has a bunch of YouTube videos that you can watch. Okay. 1, 2, 3, 4, 5 groupings of 0. 1, 2, 3, 4. 2, 3, 4. Yeah, 5 zeros. Okay. All right. And I think that concludes the examples that they show involving, let me see, scientific notation. Yeah, so this was just, I just want to make sure I got all those sheets covered. Yeah, so we should be good. I think that covered all the sheets on that, showed how to work that. I was kind of also checking the answers. Like this one needs a comma, 46,000. Okay, Cos. Let's stop here. So work on your COREC information and Connect Math.